So we had already two different processes to create bases. The first was to build it up one by one with vectors. V1, then we added another vector, and finally we stopped when we had a linearly independent spanning list, which is then a basis. The second process was to start with a spanning list, which might be too long, and then we started to cut it down until we still had a spanning list that was linearly independent again, which is again a basis. What we are missing, third way to create a basis, is if we start with not just one vector, but just a linearly independent list. So this is the third way, and this is called lemma 3.2.8. It says that every linearly independent list of vectors in a finite dimensional vector space, of course the finite dimensionality is important, it can be extended to a basis of V. So this is called extending it when you add more and more vectors. And the proof is similar to this first way, really. It's just we don't start with one vector, we start with a finite list of vectors, V1, Vk, linearly independent list, in V, where the dimension of V, let's say that it's n. We already know from our previous theorems and lemmas that k should be less than or equal to n. We also know that if k is strictly less than n, then L cannot be a spanning list. So the span of L is not V, which means then there exists Vk plus 1 vector, which is in V, but not in the span of L, in the set V minus the span of L. And then we add this Vk plus 1 vector to L to get a prime list with vectors V1, Vk, Vk plus 1. And this is still linearly independent because we added a vector which wasn't in L. And we know that this process must stop when the number of vectors reaches n. So when k plus 1 equals to n. Since we cannot have more than n linearly independent list in a vector space with dimension n. That was the statement of theorem 3.2.2. When we reach n with this, the reason we stop is because we reached the place where we don't have any vectors outside of the span of L. So that means at that point the span of L star, or whatever in special notation you want to get for this L list, at that point it will be a spanning list. Alright, so after this, these three ways of creating bases, now we return for a while to subspaces and direct sums of subspaces. First of all, lemma 3.2.9 says that if V is a finite dimensional space, vector space, and U is a subspace of V, then there is another subspace, W of V, such that V equals to the direct sum of U and W. Moreover, we also know that the dimension of U is less than or equal to the dimension of V, with equality if and only if U actually equals to V. Alright, so here is the proof of this lemma. Let's say that we have this U here, which is finite dimensional. That means it has a basis. Let's say that the notation is B stands for basis and subscript U because it's for the U subspace. And it's finite in many vectors, let's say U1, U2, UK. So this is a set notation, and sometimes we don't care about the order and we talk about the basis as a set of vectors. Let me still choose a list, more convenient to have an ordered set. So this is a basis, but it's also a linearly independent list in V. And then that means, according to the previous lemma, that we can extend it to a basis in V. So let's say that this is denoted by B with no subscript, since V is the whole vector space. And let's denote, well, first we have the KU vectors, And then the extension with some other vectors, let's denote those with w's. Let's say n of them. So this is the extension part. We create a subspace w as a span of these vectors, w vectors. And again, let me use the list notation. So first of all, v is the sum of u and w, since the basis means that it's a linear combination of u's element from the u subset, and when you take the rest of the linear combination from the w's, you get a vector in the w subspace. Also, because these are linearly independent, so b is linearly independent, that means that the intersection of u and w is just a zero vector, since b is linearly independent. That means that v is really the direct sum of u and w. v equals to u direct sum w. And we also have that the dimension of u is k with our notation of the basis vectors. It's clearly less than or equal to k plus n, which is the dimension of the v, since the basis has k plus n vectors in it. And we have that equality is there in this inequality. If and only if n is 0, that means we don't have to extend the basis with additional vectors, and that means that the u basis was already a basis for the whole space, which means that u was the whole space already. So this finishes the proof of the lemma. Then theorem 3.2.10, let L be a list v1 vk. So this is a list in vector space V with the dimension of V equals to n. Then any two properties imply the third. So interesting thing is that one is not enough. It's not complete equivalence of the three statements or three properties. You need two of them and you get the third one. And the three properties are, one is that k equals to n. That means you have as many list elements as the dimension. So if you also have that L is linearly independent, for example, then these first two imply that L spans V. Or for example, if you choose the first and the third, that implies the second. For example, the second and the third implies that this is a basis. And then the number of basis elements is unique, and that's the dimension of V, so that's why k equals n. But then just having n vectors in a list doesn't really mean that it's a basis. It's just you can have n random vectors put together. You also need that they are linearly independent to have that, then they span V, which means that it's a basis. So each two basically together mean that it's a basis. But on their own, neither of these three properties imply that you have a basis. These are all consequences of the previous theorems. Please think about this. And then theorem 3.2.11. Again, we look at subspaces. Let U and W be finite dimensional subspaces of the vector space V. Then we have this equation that says that the dimension of U plus W, not necessarily direct sum, equals to the dimension of U plus the dimension of W minus the dimension of U intersection W. So this is a kind of set theoretical calculation of dimension. The proof of this theorem, so U intersection W is a finite dimensional subspace of U and W. That means it has a basis. Let B, the basis of U intersection W, be the list V1, V2, Vk. It's a basis of U intersection W. And note that this is a subspace of U, and also this is a subspace of W. We will extend this basis to a basis in U and W independently. So in U, we will have a basis of vectors starting with these vectors and then continue with vectors, say U1, UR, and then we extend it into a basis in W. So in addition to these V1 vectors, V vectors, we have to add some W vectors. We don't know how many. Let's say the notation is T number of vectors. So with this, the picture, at least the set theoretical picture of this is that you have a W subspace, we have some kind of U subspace, and then we have a basis in the intersection. The basis is V1, Vk, and then we extend it into a basis in W with W1, Wt, and we extend it in U to a basis with U1, UR vectors. So then let's put all these together into a list, starting with the V1s, not repeating them, just adding to them the U vectors and the W vectors. And we claim that B is linearly independent. We prove this statement in this proof by contradiction. So assume that B is linearly dependent, not independent, which means that there is a non-trivial linear combination can produce zero. That means that when you take, as I goes from 1 to k, the linear combinations of V's, say AI, Vi, then the linear combinations of U's, with say Bi, Ui, and the linear combinations Ci, Wi's. So I goes from 1 to t, that equals to the zero vector. If we rearrange this, we get, let's take this to the other side, we get AI, Vi, I going from 1 to k, plus the sum of I going from 1 to r, Bi, Ui, equals to minus Ci, Wi, I going from 1 to t. These were in U subspace. This is in the W subspace. So if they are equal, that means that they are both in U intersection W. But we have that there in the intersection, the V's form a basis. That's how we started. And here are the V's. That means we shouldn't have any additional UI vectors. The V vectors should be enough. So that means all the BI's should be equal to 0 because the UI's are not needed, since V1, Vk is already a basis. That means that we have all the B zeros, and then what we have is that from 1 to k, AI, Vi, plus, again, just looking at the original Ci, Wi sum on the left hand side, that creates the zero vector. But now we are in the W space, and there, when you put together the V's with the W's, it's a basis in the W set. And if it's a basis, they are linearly independent, and the only way to create a zero vector is if they are all zero coefficients. So that means AI equals 0, I going from 1 through k, and also the Ci's are zeros, I going from 1 to t. Going back to where we started with this, so we try to assume that what if B is linearly dependent, but then we got that the non-trivial linear combination is really trivial because all the coefficients are 0. So if only trivial linear combination can create zero vector, that means that B is linearly independent. We also have that this span of B equals to the set U plus W. and it's linearly independent, and it's a spanning list. So that means that B is a basis in U plus W. That means that the dimension of the U plus W space equals to the number of vectors in the span, and that's K plus R plus T. We had for K that's the dimension of U intersection W. How can we write out what R is? If you look at the basis for U, what we have is that K plus R is the dimension of U, and K plus T is the dimension of W. Let me write this down here again on the side. The dimension of U was K plus R, the dimension of W was K plus T. So then we can solve each of these as equations and get that R is dimension of U minus K, that's R, and T is the dimension of W minus K. K is the dimension of U intersection W. So we have one positive dimension of U intersection W and then two negative. So if we write this down again, what we get is that the dimension of U plus W is the dimension of U plus the dimension of W minus the dimension 1s of U intersection W, which was exactly the statement.